Hello and welcome to Project152, your weekly specialist exam prep. Now every week we go through questions from the QCAA. If you stick with us for the whole time, you'll have done every one of the 152 questions the QCAA has ever released. We are up to week 29, which is our second last week. Week 30 is going to be the last week. We're going tech active this week. Let's get into it. So a nice little exponential distribution question here. So we've got a nice little equation here. We told the mean of x is 1 over lambda. You should already know that. All right, the mean length of time taken for students to answer questions in this class is 15 seconds. That's good because we can use that to calculate what our lambda value is. Now we're told that the mean is equal to 1 over lambda, and we're also told that the mean is equal to 15 seconds. So 15 equals 1 over lambda, which means that lambda equals 1 over 15. Now because we know that lambda is equal to 1 over 15, we can put 1 over 15 into our equation there and into our equation there. All right, so we've got a nice little equation here, and then it says the probability that the next question in this class is answered between 8 and 17 seconds is. So this is an exponential distribution function. We are going to find the area under the curve between 8 and 17 of that function right there. I won't rewrite it again because I'm going to write it in my calculator. So here's my calculator, and I'm going to go math, and I'm going to go more options, and I'm going to do the integral here, and I just type in this equation, and I'm going between 17 and 18. Between 17 and 8, sorry. All right, I've typed it into my calculator. We should be good to go. I'll click execute on that, and I get an answer of 0.2646. All right, let's take a look. See if that is our answer. Click, 0.26. Done. Relatively straightforward question, but you want to use your calculator. You don't want to do all of that by hand. Celebrate. Okay, so we've got some kind of sample mean style question here. In a town, the mean number of residents per household is 3.79 with a standard deviation of 1.47. And it says we're going to take a random sample of 45 households. So as soon as we start talking about samples, we want to jump into our formula sheet. And we know that the mean of our sample is going to be equal to the mean of our population. Now, the mean of our population is equal to 3.79. And we know that the standard deviation of our sample is going to be equal to the standard deviation of our population divided by the sample size, the square root of it. So the square root of 45. All right, so I could calculate that, but I'm not going to calculate it for now. I know it's some number. All right, what am I trying to do? Let's draw a picture of it. Our sample means are going to be distributed around our mean of 3.79, and we want to know the probability that the mean number of residents per household will be more than 4. So here's our 4, and we want to know this here. Calculator. So I'm going into stats mode here, and I'm going into distributions. We're looking at a normal distribution and just an NCD. We're trying to calculate a probability. All right, so what's my lower value going to be? It's going to be 4. My upper value is going to be like enormous. Let's just use a big number there. Okay, now what we can use here, let's do our mean first because that's easy, 3.79. Now I said I wasn't going to calculate that. That's because I'm going to calculate it in my calculator right here. That way I don't have to do any like approximations. All right, so that will give me the answer, the decimal. You can see it's all done in this one picture for me. All right, let's draw. Beautiful. And that gives us a probability of 0.1689. Do we see 0.1689? I see something very close to it, 0.17. That's my answer. All right, great little question there. Not much to talk about. Celebrate. All right, so a fun little question here. It's a related rates question, and it's a scaffolded one. So they talk you through it by asking you something in part A, and then something in part B, and then something in part C to finish it off. All right, let's just move things around a little bit so everything's a little bit bigger, and we'll just focus on part A for now and deal with that one first. All right, it says, given that H equals 2R, determine a function for the volume of water in the cup V in terms of H. All right, so this liquid in the cup, however much, we want to calculate a function, V equals, and then some function. Now, volume of a cone, it's sitting on your formula sheet. So there it is. So we'll write that down. So what we have at the moment is a function for volume, but it's in terms of R and H. And we want a function just in terms of H. So we need to get rid of this R. Now, note that H is equal to 2R, which means that R is equal to H over 2. So we can sub that H over 2 into this equation for R. So let's do that. We get 1/3 pi. The R is H over 2. I'll put that in brackets. And we'll square that because we're R squared. And then multiplied by the height. All right, what do we get? We get 1/3 pi, square top and bottom there. We get H squared over 4. And then multiplied by height. All right, we've got a height squared times height, that's a height cubed, and we've got 1/3 times 1/4. So I've got 1/12 pi H cubed. That is my function for volume in terms of just height. Now I'll just get rid of all of this and we'll move on to part B. We'll just keep that volume because we're going to use that in part B. So moving on to part B here, let's take a look at what that says. Use the results from question 15A, so use this formula, to show that the rate at which the height of water in the cup is increasing with respect to time is given by this. All right, so this is a related rates question, definitely. You should have seen one like this before. So what I'm thinking is, show that the rate at which the height of water is increasing with respect to time. Okay, so the rate of height with respect to time. Now these related rates questions, I like to set it up with a dH on the top multiplied by a dt on the bottom. And then there's some connecting variable between those two. And the connecting variable here is volume. All right, so let's look at the question because usually there's some information in the question that helps us. Water is poured into a cone-shaped cup at a rate of 2 centimeters cubed per second. Okay, that's volume with respect to time. So straight away, dV dt, we know, is equal to 2. All right, straightforward, easy, nice. This dH dV, however, that might be just a tiny bit trickier. Now what we do have is this equation here, V, and I'll just write it a little bit differently just to make my life easier. V equals pi h cubed over 12. Now, we can find the derivative of this, dV dH. Remember, whatever the function is a variable of, like that's going to be our bottom bit. And we can find the derivative of this. So the 3 comes out the front, 3 pi h squared over 12, which is just 3 and the 12 cancel each other out. We get pi h squared over 4. Now, that is dV dH. But in order to put it into my formula, I don't need dV dH, I need dH dV. So I could just flip everything here upside down and I get 4 over pi h squared, and I could put 4 over pi h squared right there. All right, this is really finished now because now we can multiply by 2. We get 4 times 2, which is 8, 8 over pi h squared, and we are finished with part B because it said use the results from question 15A. We just use the results to show that the rate at which the height of water in the cup is increasing with respect to time is given by 8 over pi h squared. 8 over pi h squared. Okay, that's part B getting rid of. Let's just, we can get rid of all of this because we've got the result there. This was the proof that that result is true, and we can move on to part C. All right, so part C is determine the rate at which the height of water in the cup is increasing with respect to time when the volume of water in the cup reaches half of the total capacity of the cup. All right, so in the previous part B, we said that the rate of change of volume with respect to time was equal to 8 over pi h squared. And even if you couldn't do part B, you know it because you're told it. Okay, now we want to know what is the value of this when we reach half of the total capacity. In order for us to, it would be tempting here, I think, to just say, oh, okay, half of the total capacity 12 centimeters, h 6 centimeters. I'll just put 6 into this equation and I'm finished. However, that is not what half of the total capacity means. In order for us to calculate half of the total capacity, we'll just calculate the total capacity and divide that by 2. So let's calculate the total capacity using the volume of a cone formula. Now I know I said I was going to use the volume of a cone formula, but how about this one? This is also the volume of our cone, and it's simpler because I just have to worry about h. So that's what I've done, 1 over 12 times pi times height cubed. I type that into my calculator and I get 452.389. Now we don't want the total capacity, we want half of the total capacity, which of course is that divided by 2. So half capacity is 226.195. Now don't forget what we're trying to do. We're trying to calculate the rate, so this value, when we're at half capacity. Now the only way we could do that is if we knew what the height was at half capacity. So we can put that back into this formula here. So solving for h, we can say that the volume at half capacity is 226.195, and that's going to be equal to 1 over 12 times pi times h cubed. 226.195 equals 1 over 12 times pi times h cubed. We can just ask our calculator to solve that for h for us. So there's my calculator. I'm doing a solve n of that equation right there. Enter, and yes, warning about more solutions, and we get an answer of 9.52. So this 9.524, that is the height that this needs to be at. So about here, if we look at our picture, that's half the capacity, right? That's half the amount of liquid. So all we need to do now to determine the rate at which it's changing when we're at half capacity is sub 9.524 into this and solve. So dv dt equals 8 over pi 9.524 squared, and calculate. And I get 0.028 centimeters per second, and that is the end of that one. Celebrate. So a fun little question here. We're looking at confidence intervals. So look at this. We've collected some data, all of this data here. There's our sample. And part A just says, determine the mean of this data. So this question, here's a sample, determine the mean of this data. This could appear on a year 8 maths exam, right? We're just calculating the average of this. Adding these together and dividing by 12, because that's how many there are. All right, so all of the values, I didn't write them all out, no point doing that. Divide it by 12, put that in your calculator, and you get 9.23. The only way to get this wrong, and I think lots of people would have, is just misentering something into your calculator. So be careful when you do that. All right, I'm going to move this value of 9.23 up to here, and we'll move into part B. So next question here is, use an approximate 95% confidence interval for the mean to evaluate the claim. All right, so let's find that 95% confidence interval. You need to be careful here. So straight to our calculator. I'm not going to use the big formula because this is tech active. I don't need it. Statistics, intervals, we're going with a Z. We're going with a sample. Okay, so far so good. 95% confidence interval. And then the mean is simple because we calculated it, 9.23. N, let's look for a sample size. So we had 12 customers here. Calculator 2.384. Okay, and then we are done. We'll come down here and we'll calculate that. And there is our 95% confidence interval. So they're the values I put into my calculator, calculated a 95% confidence interval of 7.88 to 10.58. Now, this is a 3-mark question. This is worth 1 mark. What was the question? Use an approximate 95% confidence interval for the mean to evaluate the reasonableness of the company's claim. Okay, let's see. What did the company claim? A company claims that the mean wait time for their customers is 7.6 minutes. Okay. Based on this sample, the company's claim is not reasonable. So we'll use the QCAA's answer as a guide here. The company's claim is not reasonable. This decision is justified as the claimed population mean wait time lies outside of the confidence interval. So these sorts of questions, the QCAA quite likes this kind of question where you use a confidence interval to justify a claim. All you need to do is calculate the confidence interval and say it's outside of it or it's inside of it. If it's inside of it, the claim is reasonable. If it's outside of it, the claim is unreasonable. Okay, celebrate. So a fantastic little inclined planes question here. Let's really zoom in on this though. We'll deal with this big picture here. We'll label some stuff up and then we'll start doing a bunch of other stuff. All right, we have an object here and it weighs 12 kilograms. Now, any object that weighs any amount of stuff and lives on planet Earth is going to be affected by gravity. So our object is exerting a force straight down of 12 times g, 12 times negative 9.8, straight down. Okay, when it comes to these inclined plane questions, it's a good idea to consider your I and j components like that. Okay, so the plane is parallel to our I components and our j component is perpendicular to that. Now, when you're doing these kinds of questions, you really want to break this up into its I and its j components. Now that gets a bit tricky, but basically what I'm going to do is draw a line that is parallel to our j component or perpendicular to our I component. Should look something like that. And then another line here like that. And so this 12g can be represented as a vector that is purely j component and a vector that is purely I component. Now, see this angle here? In the question, we don't know what it is, so we'll just call it theta for now. This angle can be transferred to there. Okay, now follow along. Now, because that is theta, this inside the triangle is 90 minus theta. And because this is a right angle triangle, if this is 90 minus theta, this angle right here inside the triangle is theta. Okay, it's important to know that that angle is theta. It's equal to that angle there because that lets us come up with a value for this and a value for this using trig. So very quickly, sine theta is equal to opposite over hypotenuse, where opposite, if that's theta, opposite is here, which means that h sine theta is equal to our opposite side. Now h is the magnitude of this here, which is 12g, which means that this vector right here is 12g sine theta. 12g sine theta. Now for similar reasons, 12g sine theta I in the I direction. For similar reasons, this is going to be 12g cos theta in the j direction. All right, so we have a vector 12g cos theta going straight down, if we use down as being like this angled bit, and we have this 12g sine theta I, which is a force running parallel to our plane. Our force going down here. All right, that's a nice little picture there. We can also create an interesting picture here using our string. So you can see there's a rope attached, but it's not attached from here straight to there. It's attached on an angle up there. Now we're told the force of the rope, T, prevents the object from moving. So we can say that the force in this rope is just capital T. And now, if I draw a nice little right angle triangle again, do my best. Right, now we can come up with some amount of tension in the purely I direction and some amount of tension in the purely j direction. Now this is going to be t, let's make sure we do this right, cos 25 in the I direction, and then this is going to be t sine 25 in the j direction. Okay, beautiful. If we want to complete the picture, there is some sort of normal contact force here, right? When something's touching the ground, we've got a normal contact force, but I don't think we're going to have to worry about the normal contact force at all, so we don't really have to draw it in too much. All right, that is the setup. Before I've even done any kind of like equations or anything, really understanding what all of these forces are in relation to their magnitudes and their angles, very, very important. Okay, I've summarized this and I'll move it over there and we'll keep going. Okay, so here's our little summary. Let's keep moving forward. Now, important to note that we're interested in acceleration down the plane. So our object is going to be accelerating this way, right? When we detach the rope. Bonk. Now, because we're only interested in movement in the I plane, not in the I direction, not in the j direction, we only really need to consider our I components here. And there's only two of those. So there's this one here moving in that direction, and then there's this string, so this arrow, this vector right there. So for the thing to be staying there while the string is attached, that means that this must be equal to this. Let's ignore our little acceleration arrow for now. This must be equal to this. So we get a nice little equation. We get 12g sine theta must be equal to the tension in the string cos 25 degrees. All right, so there's a nice little relationship between this one and this one here. I'm not sure it's super necessary to sort of follow this along, but let's go a different way. When the rope is detached, the object moves down the plane with an acceleration of 5.6 meters per second. All right, so all of this stuff is all in forces, and now we're talking acceleration. So let's turn that acceleration into a force. What force is required to create that acceleration on this object? All right, so we know that force equals mass times acceleration, and force is equal to, now the mass of this object is 12 kilograms, and we know it's accelerating at 5.6. All right, calculator. Now, 67.2 is the force that is required to accelerate this object at 5.6 meters per second. Now, that force is unleashed, if you like, when this rope is detached, which means that this force must be resisting 67.2. The force in this string must be 67.2. So that means that this string, t cos 25, must be equal to 67.2. So t is equal to 67.2 divided by cos 25. And let's calculate that. And our answer is 74.15, which is our final answer. Determine the magnitude of this tension in this rope. It's 74.15. Sorry, tension in this rope. Okay, 74.15. Now, in the work solutions from the QCAA, they go down a slightly different circuitous path, I think, because what they end up doing is using 67.2 to solve 12g sine theta. Because remember, I've told you that 67.2 is equal to t cos 25, but we also know that t cos 25 is equal to 12g sine theta. So you can say 67.2 equals this, and you can solve for theta, you can solve for that angle. Once you've solved for that angle, you can then put that angle into this equation and solve for t. That feels like extra steps to me that are not necessary. I think we can jump straight to solving t cos 25. Okay, celebrate. And last question. All right, here we go. Pretty big question here. Lots going on. So, the heights of Year 9 students, blah, blah, blah. A teacher at the school measured the height of all students in our Year 9 class. This data was used to calculate an approximate 95% confidence interval of this. All right, so we're thinking confidence interval, so we'll get a confidence interval formula up here. All right, the teacher repeated the procedure using data from another class although this class had the same number of students, so same N, its data produced an approximate 95 confidence interval of this. All right, so 2 classes. I can already see that we're going to end up in some sort of simultaneous equation situation probably. Let's write something down. Let's focus on the first class. Now, because the first class has a lower and upper confidence interval of these values, we can find the mean by just averaging them, adding them together, dividing them by 2. Now, I can do the same for the second class as well, adding together lower and upper and dividing by 2. Now, you might be looking at the work I've done so far and think, why? Why did you do that? Well, I don't know why I did that. I did that because I've got an approximate confidence interval formula here, and it feels like we're in that realm, and I've got some things that I don't know. For instance, I don't know that mean value, so I found that mean value. It's as simple as that. I'm looking for things that I don't know. I don't even fully know what the question's asking yet. I haven't read that far. I've calculated this. That feels good. Speaking of which, I've got these Z values here, and it says 95% confidence intervals. So I know that my Z score for both of these is going to be 1.96 because that's a 95% confidence interval. So now that I've gathered some information, let's start putting some stuff into a formula. Now, usually with these confidence interval questions, you don't have to consider everything. You don't have to consider the lower and the upper. Let's just go with the lower for now of class 1. Okay, now we do know what the lower bound was for class 1. It was 163.7. And that's calculated using the mean, 165.3, minus the Z score, 1.96, times the standard deviation of that sample divided by the size of that sample. Now, I'll admit that this next step wouldn't be my first instinct when I'm doing a question like this, but I'm going to do it now so that we don't have to backtrack. In the real world, I'd probably do class 2 first and then sort of muck around a little bit and then decide that I had to do this next step. But what I am going to do here is just get the S1 and the root n all by themselves. Just rearrange this. So it's going to be 163.7 minus 165.3 and then divided by negative 1.96. So there's class 1. We've got this funny little equation here, 0.816 equals S1 over root n. And we can do exactly the same thing for class 2. So class 2, we get 167.8 equals 170 minus 1.96 S2 over root n. Now this formula is based on the lower confidence interval, 167.8, but you can also do it for the upper confidence interval as well. Now rearranging this for S2 over root n, so the standard deviation of this class 2, we get some value as well. I'll skip this middle line and jump straight to that value. Okay, and so we've got this value here, we've got this value here. Now, why did we do that? It becomes obvious when we do this next step, and again, in the real world, it's when I'm doing this next step that I would realize that rearranging would be a good idea. So what does the question say? It says, using the same data, the teacher recalculated the approximate confidence intervals for each class using some other confidence level. So not 95, some other confidence level. We don't know what the confidence level is. She observed that the upper bound of the confidence interval from her Year 9 class now equaled the lower bound of the confidence interval from the other Year 9 class. Okay, that's the key. That's the secret. We're going to create a beautiful equation from that. All right, what does it say? She observed that the upper bound of the confidence interval from her class. So let's find an equation for the upper bound of her confidence interval. Upper confidence interval. Now that's going to be equal to the mean, so 165.3, upper, so plus, and then some unknown Z score, don't know what the Z score is, and then S over root n, or I guess S1 over root n. Now thankfully, we know what S1 over root n is, and this is where we sort of go, oh, okay, that makes sense. We had an S1 and a root n there, we got an S1 and a root n there, we can sub it in directly. So we can say that the upper confidence interval of her class is equal to 165.3 plus S1 over root n, which is 0.816, 0.16 times Z, whatever that confidence interval happens to be. Now that's her class. The other class, so we'll see like class 1. Now the other class, class 2, their upper confidence interval, or their lower confidence interval, equaled the lower bound. All right, so their lower confidence interval needs to be equal to 170.1 plus, lower, so it's minus. And then it's going to be the same ZS1 over root n, but we know that their S2 over root n is 1.173. 1.173 Z. And finally, we know that this equation, call it equation 2, is equal to equation 1. And so we set those equal to each other and we should be able to solve them. So here's our two equations. We've taken our upper here, set it equal to our lower here. And then you can just type that into your calculator and solve for Z, or you can just kind of do it the old-fashioned way, rearrange it. That's relatively straightforward. So solving that, I get a Z score of 2.413, which is this close to having the final answer. Because we don't want a Z score, we're trying to determine the value of X, where X is the confidence interval. So all we have to do is convert this Z score of 2.413 to a confidence interval. And so to do that confidence interval calculation, what you're doing is taking a standard normal distribution, mean of 0, standard deviation of 1, and finding what area exists between positive 2.413 and negative 2.413. All right, calculator. So I'm in stats modes right now. I go into distribution, I go into normal distribution. I'm doing NCD, I believe, and then we go lower and upper. So we'll go lower of negative 2.413 and an upper of 2.413 and a standard deviation of 1 and a mean of 0, and we'll draw that. And we get a confidence interval of 0.9842. So using our calculator, we get a confidence interval of, or a confidence level of 98.42%. Fun little question here, a little bit of a stretch in the middle when you're realizing that you've got to use this, but you maybe don't realize it until you get to here, but celebrate. So that is it, another one done and dusted. Join me next week for the last Project 152, week 30, done. Catch you then.